5.11, we are going to talk a little bit more about catalysts and how they work. We've seen how raising the temperature can increase the rate of reaction, but sometimes it's not feasible. One example of that is our bodies. We contain enzymes that help us to help our bodies increase the rate of the biochemical reactions, but we don't necessarily want to raise our body temperature in order for these reactions to happen. So an enzyme is like a catalyst, which helps speed up the reaction without being consumed itself. In order for a catalyst to increase the rate of reaction, it must either and or increase the number of effective collisions and provide a reaction path with a lower activation energy relative to the original reaction coordinate. So catalysts are classified as homogeneous or heterogeneous. A homogeneous catalyst is one that is present in the same phase as the reacting molecules, and a heterogeneous catalyst exists in a different phase, usually a solid. So heterogeneous catalyst is most often involves gaseous reactants being absorbed on the surface of a solid. Adsorption refers to the collection of one substance on the surface of another substance. Adsorption, we have to be careful here. Absorption refers to the penetration of one substance, like water is absorbed by a sponge. But if it's adsorbed, then that means that it's just collected, or it creates bonds on top of another surface. It doesn't go into the substance. Okay, so be careful there. So very, very close. So the steps for heterogeneous catalysts: adsorption and activation of the reactants happens first. Then the absorbed reactants will migrate on the surface to other substances, and as migration puts them together, then there's a reaction between those adsorbed substances, and then the new products will escape or desorbed from the surface. Homogeneous catalysts exist in the same phase. There are many examples in both gas and liquid phases. The picture I have here is a picture of the ozone layer, and so you might have heard, like, there's a hole in the ozone layer on the South Pole region, and so in this picture, purple means lower ozone units and green means higher ozone units. So that is an example. So homogeneous in the ozone, we will see an example of this in a second, but where they're all gases up in the ozone layer in the atmosphere, so that would be a catalyst reaction in the ozone layer. In a reaction mechanism, we know that the concentration of the catalyst, they eventually cancel out, right? So that means that the concentration is constant. However, the catalyst will frequently be consumed in the rate determining step, so it will be regenerated later. It might not be the exact same molecule, but it is regenerated, and that's how we know that it cancels away and is not a part of the overall reaction. So an example for the ozone layer, we have something that is called nitric acid, or nitrogen monoxide. We are thinking about our chemistry one naming. That's just NO. This is very good in the lower atmosphere because it actually helps produce ozone, which is O3. But in the upper atmosphere, it actually causes the depletion of the ozone. So this is an example of how it depletes the ozone in the upper atmosphere. Okay, so if the nitrogen monoxide or the nitric acid reacts with the ozone, it creates nitrogen dioxide and oxygen gas. And then the nitrogen dioxide reacts with free oxygens, and these free oxygens are created from other reactions that are happening in the atmosphere. So they're very reactive because they're very unstable, created from other reactions. RXN stands for reactions. Okay, and the products of that are the nitric oxide and more oxygen gas. So if we were to add those two steps together, we would see that the nitric oxide cancels out and that shows us as a catalyst because it was first seen as a reactant. And then also the NO2s cancel because those are an intermediate. So we have the reactive oxygen atom plus ozone makes 2 oxygen gas molecules. So this shows that even though it's not in the overall reaction, this nitric oxide is very detrimental to the ozone in the upper atmosphere, and so that's what's helping. That's one way of causing the ozone depletion. And this nitric oxide is created sometimes from reactions in the lower atmospheres, but a lot of times it's happening from our vehicles in a catalytic converter. Another type of catalyst is a binding catalyst. This is a heterogeneous example of a catalyst where they're on the surface. So some catalysts will accelerate by binding to the reactants. So the reactants are either oriented more favorably, or they can react with the lower activation energy because of the added catalyst. So often you can see a new reaction intermediate in which the catalyst is bound to the reactants. So many as enzymes function this way. Enzymes are an example of homogeneous catalyst, but surface catalyst is a type of binding catalyst, but this is a heterogeneous form. So in surface catalysts, the reactant or intermediate binds to or forms a covalent bond with the surface of usually the metal that it's reacting with, and this produces new reactions from this newly bound reaction intermediate. So I have an example here of this actually is how you change ethylene into ethane. So ethylene is a triple or a double bond. It's kind of hard to see for the picture, but you see how there's only 2 H's on that? So that means that that is 2 double bonded carbons, and then each carbon has 2 H's. Okay, but that turns into ethane, which has 3 H's on each carbon. So then that means the carbons are single bonded to each other. So how does this work? Okay, well, first of all, hydrogen gas is, it binds with, it's absorbed to the metal surface, and what happens is the HH bond gets broken, and then there is a hydrogen metal bond that is formed. And so that's what you can see right here, where the H is now stuck to the surface. It's bonded to the surface. Well, ethylene will come into the surface, and also, so if it has a double bond, remember we learned about sigma and pi bonds earlier this year. Remember that when you have a double bond, one of those orbital or molecular bonds is a sigma and one of them is a pi. So the pi bond breaks, and then so that means that there's only now a single bond between the 2 carbons, and then there are lone electrons on each carbon. And so when you break that pi bond, then where these lone electrons are, that creates bonding to the metal surface. Okay, and so then after we have the hydrogens bonded to the metal surface and the ethylene bonded to the surface, they migrate together. That's one of the steps. They migrate together, and then after they're migrated, then the hydrogens will break their bonds with the metal surface and then connect to the extra electron spots on the binding sites on the carbons. And then when there are no more binding sites on the carbons, then this newly formed molecule, ethane, instead of ethylene, will break free and is the new compound. So this is just an example of how surface binding catalysts work. But again, this is a type of heterogeneous catalyst because it's binding to the metal surface. It's absorbed to the metal surface. Some catalysts involve covalent bonding between the catalyst and reactants. When we have an acid-base catalyst, the reactant or intermediate either gains or loses a proton, which is a hydrogen ion, H+1. This introduces a new reaction intermediate and new elementary reactions involving that intermediate. The proton is attracted to lone pairs of electrons on atoms like oxygens, nitrogens, or sulfurs in a molecule. It can also be attracted to pi bonds in alkane or alkene molecules as well. So I have an example of how acid catalysts work, where we have the H plus is getting added in, and it's attracted to the oxygen in the intermediate molecule, and then that helps us form a new molecule. Okay, so this is going to be the production of ethanol from the acid catalyzed reaction of ethylene and water. So the ethylene, when you look at it just on a piece of paper, it might look like something like this. And let's draw some Lewis structures so we know what we're talking about here. Okay, so this is the ethylene, and this is the ethanol. Quick little organic chemistry side note. Anytime you have an OH group like this, this is an alcohol group. And so that's why it has all on the end, OL on the end, because that is telling you that it has an alcohol group on it. And when it has an E, an ENE, that's telling you that it has a double bond within the structure. Okay? So if we drew out the Lewis structures, the ethylene would have the double bond between the two carbons. I think it's just good to think about the Lewis structures of everything. And then, you know, water, we've drawn that Lewis structure before, because oxygen starts with 6 valence electrons. And then the ethanol has 3 carbons on the first, or 3 hydrogens on the first carbon, and then on the second carbon there's only 2 hydrogens, because on the last binding spot we have the oxygen and the water. Now the oxygen still has 6 total valence electrons, so it has 2 unshared pairs right there. Okay, so how this works is we have an acid catalyst that helps for this reaction. So what the acid catalyst means is we might have something like hydrochloric acid or like nitric acid that is going to donate the proton, the H plus, from the acid to help with this conversion. Okay, so what happens when you add that acid, that is that the H plus is attracted to the double bond, and so it makes an intermediate. And so this intermediate that it turns into, it breaks up the double bond, and so we will have 3 hydrogens on 1 carbon, and we've broken that double bond. So we have the other carbon with 2 H's, but then there's a positive charge on this side because the H plus has to go somewhere. Okay, and so then now this intermediate can react with the water. I'm just going to say H2O, I'm not going to draw the structure. And when it reacts with the water, it turns into another intermediate. So if we combine that together, so we're adding the H2O onto that plus that positive side of things. We still have the left carbon with the 3 hydrogens, okay, but on the right carbon, now we have the 2 H's, and they, the 2 H's would rather be separated, and so that's why I'm drawing them separate. And then the oxygen from the water will attach, but it's all an intermediate, so currently the entire water has just collided and attached to the intermediate we had before. And so we still have this positive charge because there's too many things going on there. Okay? And so then when you have this intermediate, then I need to erase. So Hopefully you're following along. So this is our intermediate we are currently having. Where the water has bonded. So do you notice how we created this bond here using up the electrons? We like transferred the electrons over to there. And so then this is too much work, too much. We have to make the alcohol group. So what happens is one of the H's comes off with the positive charge. So, and that by taking those off makes the ethanol that we started with. So there's that, and then we have our oxygen, and we have our hydrogen off of that. And so then electrons, the oxygen gets back to having what it wants, and then as a second product, after they've come apart, then we have that proton again. So this proton is not the same necessarily proton that it started with from the acid, but it helped create those intermediates to turn the molecule into the new product. So hopefully before the AP exam we'll talk a little bit more about organic chemistry, and these shapes might look a little better to you later on with that.